I've been accused in the past of teaching like lame stuff for script kiddies, and that's absolutely true tonight. We're going to hack games because I think it's very good. This is how people learn binary analysis when they were just teenagers. They cheat at games. And I highly recommend it to get started with binary. I'm trying to, instead of jumping into IDA and having half the students just quit, I want to get there the way real people do, which is you start with much simpler tasks in Olly until you get sort of used to assembly language before you assault your brain with IDA. So, Olly's where we are here. Olly's a standard tool used to debug. It's an old standard hacking tool for 32-bit code. It's been around for a long time. It was purchased by Immunity and rebranded as the Immunity Debugger. Immunity's probably a better product, and one of these days I might just rewrite all my projects to use Immunity. Immunity is almost exactly the same. All the menus are the same and everything, but Immunity is being maintained. This is pretty much over. But it still works perfectly fine for 32-bit code, and it's the standard, and I've been using it. They updated to OllyDbg 2, and it's just awful. It just doesn't work. It's amazing. Later on, we're going to do a demonstration where we use this Windows API call function called ntohl, which just reverses the order of bytes from network order to little endian order. And it's totally present in this library, but if you open this library in OllyDbg 2, it's not there. I don't know how you could make this mistake if you wanted to. It's right there in the header of the file, the list of functions, and it's not there. So OllyDbg 2 is a sin and a shame. 1.01 is fine, or 1.10 is fine, and Immunity is what you use if you want a more modern thing. Don't waste your time with the in-between product where they seem to have fallen off the rails. Perhaps that's why they sold. They were going broke, they updated miserably, they sold it to another company. So anyway, if you want to debug malware, you got to get it executable. So we've talked about this. If it's an exe file, you can load it directly. You can load DLLs directly into OllyDbg. A DLL cannot run all by itself, but OllyDbg will automatically execute run DLL to run the DLL. So you can also have something already running and attached to the running process. All debuggers support that. So you just open it with file open, and it will load the thing, get ready to run, and break at the first instruction in main. So it will not actually run, it will get ready to run, so you can look at it and break, because presumably you put it in a debugger because you're planning on inspecting it somehow. So before it runs, they want to give you a chance to look at it, set breakpoints, adjust things, you know. You can always run it if you want to, but it will first give you a chance to mess with it before you run it. What's very strange is that, anyway, GDB is different, but it does amount to the same thing. All right, anyway, you can attach to a running process the same way. It will break in and pause the running process on all threads. It will stop providing service and pause in the debugger so you can mess with it. So you can reload a file. You very often have to do this. You let it run, you modify things as you run, you decide, well, this is no good, I want to start over. So you restart with Control F2, which will reload the current executable. F2 alone will just set a breakpoint, will not reload it. We've talked about the interface, you've been using it. Here's the disassembler with the address, the hexadecimal bytes that make the instruction, and the mnemonic and parameters here that run the assembly code. Over here are the registers. This is the stack, which often contains pointers to things, and it'll have a label there telling you what it's pointing to. And here's a memory dump in hex and ASCII of anything you choose to put there. You can modify data in both of the left panes. You can, in the disassembler window, you highlight an instruction and press spacebar, and you can type in a different assembly language instruction. We've done that. You can right-click and modify in the registers, or the stack, or the memory dump. So you can change them, and you can right-click any address anywhere and follow in dump to put it down in the dump if you wish to see what's there and modify the stuff in that area, and that's the point of it. You can modify the code almost any way you want to make it do what you're interested in. You've got a memory map. We're going to play with this quite a bit more. You go to View Memory Map, you'll see all the memory segments that are allocated by this code. So the libraries and such have segments, and the main executable has got its segments here. So it's got a PE header, which we talked about, which is just that text document that lists the libraries and such. Then it's always got a text segment, which has the executable instructions, and almost everything has a data section. Some things have an RData section, a resource section, a relocation section, and you can have as many as you want, but everything pretty much has to have a text section, and almost always has a data section. The text contains executable instructions, and the other things contain data it uses. And each one of these has permissions, which are like this one here. The text section is read and execute, but not write. The data section, this is read and write, our data, and this is read. So the general Windows security model is write or execute. You don't put both write and execute on the same segment because that's what leads to buffer overflow attacks and such, where you overflow a variable and then you execute that as code. Yeah.
In that, so you're able to change the permissions.
You are.
And if you recompile that code, does that actually work?
Yes.
Okay.
The Windows does not forbid you from breaking these rules, and we do it in the exploit development class. You can even run a Windows API call at runtime, and you can change the permissions, and you can allocate a new section of memory and break the rule and make it both writable and executable.
Okay.
It is an option. It's just considered a poor practice. So commercial code will not do it much, but you can totally do it. Rebasing is an issue. When you load a function, I mentioned before, all Windows executables think they are loaded at 400,000. They all think they're at the same location. It's called a virtual address, like a virtual machine. They have their own address space, always starting at that same address. They're actually all loaded in different places in memory. But DLLs, they have a preferred base address where they'd like to load, and if you support address space layout randomization, they'll often be relocated. So EXEs are almost always relocated, but DLLs are also relocated. Your libraries, when you relocate things, it makes them slower because it has to keep adjusting addresses when they load. And so it's considered kind of unwise to make all your DLLs load on top of each other and have to relocate a bunch of them. So Microsoft knows this, and they give different base addresses for all the DLLs. So all the Windows DLLs can load and not be relocated very much. Other companies may not do that. It doesn't make a huge difference, but it's considered sloppy and inefficient to make things rebase more than you have to.
So you're saying that DLLs are always loaded in the same area of memory?
Yes.
Every time?
They have a preferred location, but of course most of them are now also subject to address space layout randomization.
Okay.
So I think they'll be changing all the time anyway.
So
but I think that might happen at a different level than the rebasing. I'm not really quite sure. It'd be something to look into, and I don't quite get it. It seems to me like ever since ASLR, everything should be rebased all the time. But I think there's two different levels of virtual addressing. So absolute and relative addresses, for example, if you have code like this moves into a register, something from a register, so it doesn't matter where you are. The registers will just follow to wherever you are in memory, and this is the same. And this is a jump not zero, but this is a close location. So this is 40120A, and this is 40120. So I think it's probably a typo or something. I think this is missing a digit. This is 2467. Yeah, but anyway, I think the point is this is supposed to be nearby. And if you jump to a nearby location, less than 128 bytes away or maybe 256, this is a relative jump. It doesn't jump to this absolute address, it jumps forward by a certain number of bytes. So this will also relocate, but this one won't, where you refer specifically to an address. And so it will take time to modify this instruction if you rebase. The rest of it will just relocate harmlessly. And so these are called fix-up locations, and that's what's in the relocation section of the header. These are all the instructions of what has to be patched because I had to relocate this code. And that's what's considered sort of sleazy and unprofessional to make it do this more than it has to. And that's the game. So you can't predict where DLLs will be located if they're rebased. And we've got a relocation section here. If you view metadata parsers.dll, you can see there is a relocation section here. So this has been relocated, and it has a bunch of extra adjustment parameters in that relocation section which are used. So when you try to run a function in that library, it has to do some more work to set it up for you to use it. So that's DLL rebasing. You can remove the relocation section from a DLL, and then it can't be rebased. This might make it run faster, but it will always load in the same place. Seems like it would undo the value of address space layout randomization. This is why one thing I've said before, if you look at Internet of Things devices or cell phones, the security is often very bad because they do things like this to make it faster and smaller. They go back in time to reproduce old vulnerabilities because, of course, they're trying to make battery life, and they're sacrificing security for more performance. So here's DLL A and DLL B, both want to load at the same location. So DLL B is relocated to a different part of memory. This one gets to load where it wants to be. This one has to go to 340,000 instead of a million. And so now it has to use its relocation section. And that DLL, technically loading the same function in the other DLL, would take more steps. So IDA Pro, this is one thing that's pretty annoying. If you use OllyDbg and IDA Pro, they don't have the same addresses. And by the way, if you open the file in HXD, it's not the same either. Very annoying because the actual segments are loaded in different places in memory, and IDA doesn't know about rebasing because the code is not really running. Olly connects to the real running code, so it shows you where it really is. So you can use an optional manual process to load things in the right place in Olly. It's just a thing to be aware of. Addresses do not move from one product to another the way you think they ought to. So you can view threads inside OllyDbg even, and you could even stop them or kill them. Threads are little pieces of code. Threads are the actual pieces of the actual units in Windows that get CPU time. Your process is broken into threads, and the threads get their turn at the CPU. A very simple process might just have one thread, but mostly they have multiple threads, so that if one thread is waiting for something slow, like user input or network traffic, the other threads can move forward. That's the idea. And the whole point of all that was to try to adapt to multiprocessor computers, which I think has largely been a failure. But Intel found about 10 years ago that they could not make the clock any faster because of heat dissipation. The CPUs would burn themselves up, so they peaked at like 2 or 4 gigahertz, but the only thing they could do was put more cores on the chips. So they had 4 cores and 8 cores, and that would only work if your programs were actually multi-threaded, so all these different threads can move forward, and that has largely been a failure. Except for computer graphics, there have not been very many jobs that people actually want to do that really get use of those cores, so it is not, 4 cores does not make you 4 times as fast as 1 core for normal work, not at all. And that is a huge problem. And the only, nobody knows quite what to do next, but one thing to do next is go to straight optical computing, where you do not use electricity anymore. Everything is light, so it doesn't generate any heat. And then you might be able to make it faster. And people have developed those chips that make signals of light and flip them and do not and or, but they're not yet available in quantity cheap enough. But that's one direction to go. Yeah.
Who breaks the program into threads? Is it the actual microprocessor or is it the operating system?
It's the operating system and the compiler that has to do it.
Got it, okay.
Because your coder probably isn't willing to write a whole different kind of code. That would do it. And so that's the problem. It has turned out that taking code and trying to recompile it into multi-threads is not very effective. Yeah.
I think they also do it in the CPU too. Because
Yeah.
they sell it, even the Intel chip, they sell it like per core, how many core, and then they have like 4 threads per core.
Right, and so it's trying to break the job up, but the problem is by the time it gets code, it doesn't really know what sections are
Inside the
independent.
hardware, they have special space for cores.
Yeah, it's a good point.
Threads, yeah.
They do something, but the end result is it's not so good as it should be, and the computers in a way are not really continuing to get faster as much as you might think. Each thread has its own stack. You can see them here. So stack of thread 2, stack of thread 3, and so on. Anyway, so if you want to execute code in OllyDbg, you typically use F9 to run the prod. F12 will pause it while it's running. You can run to a selection, click a line and run there. You can run, you can execute till return with Control F9, execute till user code with Alt+I, which is good if you step and now you're in some library, like a Microsoft library, you want to get back to the user code because you're not interested in trying to debug the operating system, which is normally the case. And then we talked before about step into and step over. You're in a main function and you step into, if it calls something, you'll go into there and stop. Step over will go in and return back to the same level. So typically you step into at the beginning until you get down to the depth of subroutines appropriate for your analysis, and then you step over to avoid having to step through all the Microsoft system routines that you probably don't care about. So you can actually run the program and hit pause while it's going. This is, of course, incredibly sloppy because code's doing thousands of operations per second and you're not going to be very accurate at stopping it. Another thing that I've used more effectively is to just single step through programs. I've even done, when I first started doing Minesweeper, which we're going to do later, I just hold down F7 for like 15 seconds and see the box pop up. So then I'd hold it for 10 seconds and then one at a time, and then put in a breakpoint, try to get close, and then single step to hit the point of interest. This works. I've done this quite a lot in CTFs and other problems. If I can't read it and figure out where the breakpoint is, I'll just run it until I get close and then manually stop kind of close. And then you can single step through 100 instructions pretty fast and get yourself close to where the problem is.
What was the key for the single step again?
F7.
F7, okay.
F7 to do a single step, F7 or F8. F7 will step into, F8 will step over. Either one of them is pretty good to take one step at a time. And I've even put in run and pause and then do single step 50 or 100 times, then put in a breakpoint, then delete the other stuff and run to the breakpoint. You're just trying to get a breakpoint somewhere near the interesting point. And then you may have to do 30 or 40 F7s to get to the crash. Then you can find the crash and find the code near the crash and begin to see what you got. So you can run, to resume execution after a breakpoint, you can run to selection. If you found an interesting spot and you don't want to set a breakpoint, you just want to pause once, you can select that line and run to selection. Just a single-use breakpoint, essentially. You can execute until the current function returns, which is fine. Although, of course, all these may hang if something never ends. Execute till user code, we talked about, gets you back up into the text section from wherever you are in some DIL or something. And you can single step or step over. F7 and F8 is what you mostly do. So, of course, these are fine for normal programs, and there is, of course, malware that does every evil thing, including calling a function and never coming back because it does something like notice you're in a virtual machine. When I went to this malware analysis workshop in San Jose, and I went to another one last week, people were talking more and more about malware that knows that you're in a virtual machine, or that you have a debugger and refuses to do the bad thing under those conditions. So there are now some libraries you can add to try to hide the fact that you're in a debugger and such. All right, so I've got some cahoots about that. So, which key press steps over? This is usually the most useful one, F8. Moves you along to where you want to go. Which one modifies a line of assembly code? Okay, that's spacebar. All right. Which one sets a breakpoint? F2. All right. And which one will run until user code? Okay, that's Alt F9. F9 would run, Alt F9 goes to user code. So let me record the winners. There we are. All right. So the 4 kinds of breakpoints, we talked about them before. Software breakpoints are the most common, where it just puts a CC byte in the memory so it breaks. Hardware breakpoints are processed by special registers in the processor, so they do not modify the code at all. The only problem is you only have 4 of them. And then there's conditional breakpoints and breakpoints on memory, which are both sort of buggy, kludgy things added by the debugger at the level of Python, where it does something to try to create a break under certain conditions. You can view them with view breakpoints, or there's a B icon for them. This will show you your breakpoints down here. Here it's showing you int3 breakpoints, which is usually what you have. That's the common type. Most of the time you just use int3 breakpoints. Occasionally you need the other types. So the software breakpoint is by far the most common. Conditional breakpoints have some kind of condition under which it will break, like some memory value greater than a register or something like that. The hardware breakpoints are actually turned out quite useful to me in the project I was doing today. I was trying to modify Minesweeper, which I was not able to do, to start with more mines, because I got the idea from the Flare-On Challenge. The Flare-On Challenge, I did the first 2 levels, and they both, it appears like the Flare-On Challenge is all Minesweeper this year. The first 2 levels are Minesweeper, first in Java and then in C++, Visual Basic, and in both cases the game is just impossible. They'll start you with a board like 15 by 15, and it's all full of mines. There's like one spot that doesn't have a mine, you can't find it, because the whole point is you got to cheat. So they made the game absolutely unplayable, and I wanted to do that to you, but I couldn't find how to turn up the number of mines. So I was trying to hunt for, it starts out with 10 mines, so I was finding places where it stored something 10 in the data section and trying to change it, and I couldn't find it, so I changed it to 12. Then I looked for all the 12s, I found 3 of them, and I put hardware breakpoints on them so it would break when it tried to write to those locations, but I still couldn't find out where it was getting those numbers from, and I did not give you that challenge. If I ever get it working, it'll be another project later. But anyway, there's a Minesweeper challenge, which I think serves the purpose tonight. But anyway, that's the game. You can have memory. You can have a memory breakpoint on access. I tried using these, and they totally didn't work. And the slides warn you, these things don't work very well. And boy, they sure did not work on my Minesweeper. I put these on, and it didn't even break. So I put on hardware breakpoints, and that broke. And the point was, I did not have the instruction. I had the location in memory where it's changing something, and I want to break when it tries to use that memory address to read or write. And that's what these 2 can supposedly do, and I was able to succeed in making it break at that point with the hardware breakpoint, but not with the memory. Anyway, so supposedly it saves breakpoints when you save your file. When I keep reloading and it doesn't happen, and when you save the executable, it doesn't. But anyway, so software breakpoints can have things like you can obfuscate strings, for example, where this horrible mess will be decoded, and so you'd want to put a breakpoint in at the moment when it's turned into readable text. And that's one of the reasons you might use a breakpoint, of course. There was this project where you did this in Jasmine. Conditional breakpoints will break only if a condition is true. So you can set a conditional breakpoint at a function that will notice when it is trying to allocate more memory, which is what I was saying before. This is a common trick to get around those protections, is to allocate another region of memory and give it the permissions you want, like write and execute, and then put your malware there. So you might want to catch when that function is being used. So normal breakpoints, you just put a standard breakpoint at the start of the function, and then every time it allocates any memory, it will break, which is going to drive you nuts, because one of those is the one you care about and the others aren't. So what you want to do is make a conditional breakpoint, and only when a certain parameter is bigger than 100, which is only going to be, I think, for memory regions that are bigger than 100 bytes being allocated, which will more likely be the interesting ones. That's the kind of thing you can do with conditional breakpoints. And what it does, of course, is put in an int3 breakpoint, go back to the debugger, and the debugger checks the condition, and if the condition is not satisfied, it presses F9 for you and runs again. So that's all it's doing, but at least you don't have to do it. But it does mean, of course, that if it really has to hit this 1,000 times before the condition is true, it's going to be really slow. Hardware breakpoints work right in the processor, work fast, nice and strong. You only have 4 at a time, but they'll totally hit when you execute or when you read and write a point, when I did it. So that's very nice. I appreciate it. Built in the processor. It's not a feature of the debugger itself, so it runs very well. All right, and yeah.
The processor limits it to 4?
Yes. It uses special registers. I think DR7 or something. There's only enough room for 4 of them. And it has some attempt to protect them from unauthorized modification too. We were talking about it last week. So they're not perfectly protected from modification, and they're not perfectly flawless, but they are pretty good. So and there's memory breakpoints that can supposedly break on execution and such. These are the ones that did not work when I tried using them, and they warn you that they're not going to work very well. They actually do this by trying to change the permissions of the memory location and somehow catch the exceptions created by that. And in practice, doesn't work very well, as you might imagine. So I did not get any good out of it, but it is an option and maybe some conditions under which it's worth using. So anyway, if you want to find out, for example, when a DIL is used, you go to the DIL text section, and then you could set a breakpoint on access. And it'll now break every time execution ends up in the DIL's text section, anytime any of that DIL code is run. That's one way to get there. And the point here is you didn't know exactly what address you wanted to put a breakpoint on, so you put an execution breakpoint on the whole section. All right, anyway, so I got some more Kahoots. This is good that we're moving right along, because the project is lots of fun. I had spent the last several days writing a new project, and I think it'll be fun. So what kind of breakpoint can have no more than 4 of them? All right, those are the hardware breakpoints in the registers of the processor. What's the most common kind of breakpoint? A good old software breakpoint is int3. You have to put it in where an instruction is, and then it will execute that instruction and break. You cannot put it so it triggers on read or write of memory location. It has to be in the text section at an executable point, but that's usually the situation, and that's the most common thing to do. What kind of breakpoint lets you have only one? It was those memory breakpoints. Not only do they not work, but you can only have one. So anyway, all right. If you do want to debug a DIL, you can just click File Open in Olly and load a DIL, and it will just prompt a box and say it's going to run loaddil.exe, which is a Microsoft utility just for this purpose that will just create the necessary exe shell to load the DIL. Now you can run it. So let's try this, because there are a few little gotchas. So here's a perfectly good DIL, ws232.dil, which has networking functions. So let's open it in Olly. Here's my machine. Here's Olly all ready to go. I can click File, and actually it might be remembered. There it is right there. C Windows System 32, ws232.dil. I loaded it earlier today for practice, so I can open a DIL. Now it's just going to load with no drama, which is not very interesting. Let me do it the hard way so I can show you the drama. Is there such a thing as close? All right, now it's just going to open. There, System 32. these are exe files. I got to go to DLLs and then go down to WS232, which is going to be around here. There it is, WS232.dll. So I open it. Now that's what I wanted to show you. It's a dynamic link library. You can't execute a DLL directly, but it will automatically load DLL for me. So I say yes. Now it's going to warn me that, of course, the current process is going to get nuked by loading a new process on top of it, which is fine. And so now I've got a DLL. Now, the DLL is technically loaded, but in practice, I can't do much with it. So let me bring this up here, and I guess that'll do. Let's go back to my slides. We're going to see some trouble with these DLLs. All right, so if I want to see the export table so I can see the functions in the DLL and start using them, I can't do it. I can click Debug and call DLL export, and it's just going to tell me you can't do it. Entry point of debug DLL, you're not allowed to do that. The problem is, this is a thing to know about DLLs. DLLs, you can't just load them and use them, you have to run DLL main. When a DLL runs, DLL main is what prepares it by offering all these functions so they can be used. So the first thing you have to do is run DLL main, and I'll have to do that with the run button. So watch down in the corner, entry point of debug DLL, that message down there. When I run this, now it says initialization of debugged DLL finished. It just ran DLL main, which prepares the DLL for use. And this is what we're going to do in the malware we use later. It's going to be a loaded DLL. It always runs DLL main right away, so you can put your malware there. And it will automatically run when the DLL is loaded. That's commonly what you do. And anyway, now I can hit debug. Call DLL, all right, what's wrong here? Let me find my instructions. Now I should be able to debug, call DLL export, and it should work, which does not seem to be true. Initialization finished, debug, right. Well, that's rude. I'm just gonna try restart and see if I can figure out what the heck. Yes. Now, entry point, run, debug, call DLL export. Okay, I made it somehow. So now I have the exports here. Here's all the functions this has. This is the networking library. So it's got things like bind and connect and close socket and so on. And the thing we're going to play with here is ntohl, which is the very simple function, just so we can see how it goes, is the function that just takes bytes and moves them from network order to the other order, little endian order. So you can run a function here without having exe set it up. You can set it up yourself. Here's the registers, here's the command line arguments. And in this function, I want one argument, argument 1, and I want to put in an address like 127.0.0.1, and then I just want to run it. So I can call it here, and it will call the function, and when it's done, argument is 1 extra characters on line. So something bad happened here. Oh, maybe I got commas? No? All right. Let me go check my no arguments. Let's try this. Yeah, there's an argument, 127.0.0.1. Okay. And maybe I've done something wrong here. Call, nope, won't run. Anyway, let me go to my slides and see if I can figure out what happened. I did it right before class and it worked. I assume it may have something to do with the fact that the first time I loaded it, it wouldn't run. Something's going wrong. It looks like this. So then you put 127.0.0. Oh, it's got to be in hex without the dots. Okay, 7F0001. Okay, fair enough. It's a memory. It's a hex memory value. You can't be putting it in that way. That makes complete sense. Okay, that's why it thought I had extra arguments. It didn't know what I was doing. 7F000001. That's more like a proper hexadecimal argument. Okay, so now I can call it, and when I call it, I now get, this is the output in EAX, 010007F. It just reverses the order of the bytes. Not very exciting, but it does show you how to call a function in a DLL without any EXE if you want to test a DLL in isolation. All right, that's the game there. And like I mentioned before, if you use OllyDbg 2, you cannot do that demo because the function is not there, which is too lame for words. Anyway, then you can trace where you're going. There are various kinds of trace available. If you are running a program, you can just hit the minus sign to go back a step, and it will show you where you came from. So if you're somewhere, you say, wait, it crashed. Where did I come from? You just hit minus, and it will show you where the last few steps were. It does not roll everything back like the register values, and you cannot go back 3 steps and run from there forward again. Like you can in Microsoft Word. You can do undo, 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 and then go forward. You can't do that in a debugger because that would be way too expensive to keep track of that kind of information. But you can move EIP back to see where it came from, which is handy. That's a standard backtrace. So that's what you get if you just press the minus key. The plus key will take you forward. You cannot resume execution, but you can see where you came from, which is handy. The call stack trace will show you where you are. Remember, the way this works is your operating system is running, then you call main, then main calls subroutine, subroutine calls printf, printf calls something, and you're 4 or 5 levels down, a dream within a dream. That's the call stack, all the functions that are running. If you launch main, I'm still running main. When you call your subroutine, main is waiting for you to return from the subroutine and resume. All those functions are on the stack waiting for you to come back. And that's what the call stack does, is show you the stack frames. So we'll see that, and let me just do that here. I can do it with anything. I'll just do it with my Minesweeper. That's what I've got. So my Minesweeper is here. I'm going to nuke what's there, and here it started. I'm going to run it here. Now if I just run it, it's going to pop up a box and start playing Minesweeper, and now I went too far. I ran a bunch of routines, finished, and came back. So right now the call stack is not going to be interesting. If I try to view it, view, call stack, there's nothing there because I'm still back in main. What I need to do is debug, restart, and if I wish to see the levels of this, I need to move forward with F7, which is step into. So I'll press F7 a bit. So here I am, here's F7. Okay, now I'm stepping forward, and here I'm about to return from something here. So I'm inside some kind of subroutine. So let's try the call stack right now. View, call stack. There you go. I was in MineSam 100-400C, and now I've called from this into that. I'm in one subroutine of the program. Now if I keep on going forward, let me go back to my CPU window, which is the main place you normally stay. F7 again. Now I've returned. Now I'm back up here. Now I called into something else. And I've jumped into the kernel. Now I'm actually out of my program into kernel 32. This is what I've said. I've now left user land, gone into kernel land. I probably don't want to analyze this code. Unless I'm trying to find a kernel exploit in the Windows operating system, I've wandered off into an area that's not interesting, and you can see it in the call stack. If I go view, call stack, now I'm in the kernel called from MineSam. So depending on how your program is designed, you might be able to see 4 or 5 layers deep. This one here seems to be kind of shallow for the part I'm looking at, but that's the point. So if I want to get out of here, another thing I might try is going back. So let's go back to CPU, and right now I'm here at 7. If I hit minus, it's going to go back. Now it's faded, meaning I can't resume execution here. I can keep hitting minus. There, now I see where it came from. Here's where it called some kernel routine, get module something, so I can go back and see, maybe I want to go back and put a breakpoint here and start over. Now that I've ended up somewhere, and I want to go back to whatever user land code brought me here. So that's pretty cool. Yeah?
So I've seen pictures of IDA Pro where it's like a cell of assembly and then it like draws an arrow to another. Is
Right.
that basically like visualizing stack trace?
Yes, that's called, no, it's not, that's not a, yes, you could call it, it's more than a stack trace though. When IDA does that, it's not just calls, it's if statements. If it goes here or here, it puts them in boxes. And by the way, Olly does it too in a much simpler way over here with these little gray things on the left. Like this here shows you the functions that are going to be there. And if you have a loop, let's find a loop here. I'm going to hit F8 now. This actually, and let's jump around with F8 until we get to something more interesting, and we will see a loop eventually. There's a loop, and I'm not seeing what I expected to see here. Usually there's like gray lines here showing you the structure. Here I just see these dot, dot, dot things, but I'm not quite sure why I'm not seeing it. I often see little lines connecting things. This is a loop, this is a loop, which is a little bit like that graph, that stuff you were talking about. Somehow I'm not seeing them here, but I do see them frequently when analyzing code. Yeah, up there they are, there. like that. That shows you that this whole region has a return. This is like a subroutine. And it tries to guess what parameters come in and all that. So it tries to help you this way. It puts brackets around things that belong together. And that is the simple version. That's what IDA does, is put those in little boxes and connect them with lines. Olly will do this to help you understand, and especially this, which is very helpful. It'll try to list the parameters, and you get a clue what's going on. It helps you very much when you're trying to guess what these functions do. So this one in particular, for example, this one has a parameter null, a parameter 258. This one has 258b. I mean, it's not too obvious what this is. Actually dialog box param w. That sounds like a Windows system call. Looks like one. So you could actually Google that and get the Microsoft documents. It will tell you what it is. This is going to pop up a box of some sort, and that's why they're red. The ones, and even the ones that are not documented by Microsoft, Olly will try to guess what they do and try to help you. Like down here, I had some MindSam routines there. This is just part of MindSam, and all it's going to tell me is a 5 went in there and it called something. This just passed 5 to some other function. It was not terribly helpful, but it's doing what it can for me to help me understand these things. Post message. Some of these, it knows what they do. Some of these, it's just mind function, but at least it shows me the arguments. And I tried to use this logic to find out where it determines how many minds there are, and I couldn't find it. Somewhere in here, there's a constant or immediate value of how many minds there are, and I couldn't find it and change it yet. Anyway, all right. So if you do this one, you can step into, this is the one with the launch codes that we were doing last week, and you can see it get 2 or 3 deep in the stack here. All right. Anyway, you can return from things, and I was even able to get the call stack pretty deep at certain points in that program. I'm not getting them that deep in my Minesweeper, but you know, you can be very deep, 30, 40, 50 layers deep until you run out of RAM. There's no real limit. It's just stacking up the stack frames on the stack. There's no reason it can't be 100 levels deep. In principle, it could find its way back as long as nothing goes wrong. Then you can actually do a run trace, which more or less lets you really do that undo like Microsoft Word. The run trace, you have to turn it on for certain code, for a section, because it's too expensive to run for your whole code, but then it will actually try to remember everything. I still don't think you can go back and change your mind and run differently, but what it does do is load all the registry values for every step of the way back. So you can go back and see exactly why you ended up where you are. The other one just takes the EIP back, so you see where you were, but you don't really see all the parameters and everything that you might need to fully understand what happened. And so I'm not going to do it, but...
That's the difference between trace and run trace?
Right,
Okay, got it.
yeah. Yeah, backtrace is always on, and it's just going, minus sign will take you back, but a run trace you have to turn on especially, and it keeps track of everything, and that of course is going to slow you down and use up memory and everything else, so you use it sparingly. All right, and I did a run trace of just this in a previous demo, but it's not that interesting. I'm going to not do the demo live tonight because we got other things to do. Anyway, all right, but this is the run trace, and you see it has all the instructions and the modified registers and everything. You can get a whole printout of every command and where it went, which will help you, if you have a serious problem you're trying to debug code. And you can even trace into and trace over functions. Instead of step in and step over, you can trace over the function, so it will go there, trace everything, and come back. And then you can go back and examine every step, step by step, to really find out what's happening. And of course, this is for primarily for real debugging, where you want to find a crash, but of course it's useful for us too, where you want to exploit a crash, which is very closely related. And you can debug until a condition is hit. Just like you can have a breakpoint on a condition, you can have a trace until a condition. In principle, there's no reason you can't. And it might be necessary for certain situations, like they say poison ivy shellcode. When it reserves memory in a certain region, that's where something good is happening. Anyway, then there's exception handling. We've already played with this a bit, maybe not yet in this class. I guess it's coming up. In the exploit development class, we're going to do a lot of this. The exception handler is one of the handy ways to take over a machine. It's a place you can, it is fairly common that you have a vulnerability where you get to add code that ends up in the exception handler. So that's where you get to usually control the EIP if you just trigger an exception by doing something illegal. And so when you do have an exception, it goes back to the debugger, and you have to press Shift F7, 8, or 9 to pass it back to the program and let the program try to handle it. And that's what you typically want to do in a SEH exploit, which we'll be doing in the 127 class on Saturdays. All right. And then you can patch code. You've already done this. You can press spacebar or hit a symbol, and you can modify lines of code one by one to do different things. And you can fill memory with zeros, fill it with nops. You can save patched code by right-clicking and save to the executable, but you have to do it segment by segment. If you change the text segment, you have to save it separately before you go changing the data segment and save it. Otherwise, you'll get only some of your changes, which took me a long time to learn. I couldn't find that explained anywhere clearly enough. I just got very, very frustrated. For a while, I think the first time I taught the malware analysis, the exploit development class, I actually had people using Olly to figure out what to change and then using HXD to change it because I could not figure out how to save the changes. I felt pretty dumb, but this happens a lot. Frequently, I feel like I'm dumb because there is some cooler way to do it that I can't figure out and I have to do it some screwy way, but that's where it is. I don't think that will ever change. You're just getting a assortment of tools. A bunch of tools do similar things, and however you're doing it, there is some guy at a con that will have some great way to do it that is a lot cooler than your way, and that's fine. You just have to pick up whatever you can and keep moving. All right, here's a way to analyze shellcode. If you have shellcode in hex and you want to analyze it, you can just put it right in memory. You can allocate memory in the debugger and put it there and run it, which is kind of awesome. What most of the time I would do is write a little C shell. That's what we do in the exploit development class, write a little C handler, then compile it with GCC and run it, but you can actually do it directly in the debugger if you want to. Reserve memory, make it executable, put the shellcode in there and run it, which is kind of cool. That's sort of like that loading a DIL directly. It's using the debugger to put the shim code to get something running. Anyway, you just put the EIP at the start of your shellcode and let it run. It might be useful. One use of this might be a thing I learned to do in GDB. When Metasploit shellcode doesn't work, which happens a lot, you often want to run it and find out what the hell. And the thing I learned that really drove me nuts is some Metasploit shellcode swells during unpacking. So you actually have to have a NOP sled around it or it will destroy itself, which is very rude. And this kind of thing you find out by really running the shellcode step by step in a debugger so you can find out why is it crashing. Metasploit shellcode crashes a lot. It fails a lot. All shellcode suffers from the fact that there's no error handling. So if anything is not exactly right, it will just crash and die and not give you a clue. So it's frustrating when your exploits fail. The shellcode gives you no help at all. You are supposed to be able to figure it out because it's totally optimized to be small at the expense of all error handling. Anyway, you got a log which will show you all the steps, the file you opened, all the libraries that were opened. It shows you all the modules that loaded to get you where you are. So you can find out what happened. There's a window called watches. You can tell it to watch a certain expression and just keep a log of all the changes in that expression. So you can find out, where did this value come from. This might actually makes me think I might want to, if I could figure out which command writes the number of mines, I could then go back and watch every place that changes and maybe eventually hack down which blooming instruction sets the number of mines. Anyway, I've been struggling with this for days. It's on my mind. Anyway, so you can label things. We do this more in IDA, but you can do it in Olly too. You can assign your own labels to things. And there are a bunch of plugins like Metasploit and OllyDbg and Immunity are platforms, and you can add more code. You can write your own module just like you can write your own Firefox plugins and all that jazz. There's a bunch of people have written things to help it do special things. Here's something that will dump it to a PE file. Here's something that will hide the debugger from debugger detection. And more of that was going on at the IRCon I went to. You can control it from the command line, which is pretty interesting actually. I might have been able to use that for your project instead of using proc dump. There might have been a way to dump from inside Olly from the command line, which would have been cleaner. But anyway, and you've got bookmarks, There's writing your own plugins is another cool thing to do, and you can write your own scripts to script your debugging. I've done a little bit of this in GDB. I haven't done it in Olly, but it's totally there, and I think your scripts are in Python, so you can automate it to do complicated things, and that's pretty cool. So you could automatically do a repetitive series of tasks. Anyway, I got some more Kahoots, then we'll take a break, and then I will show you the Minesweeper project. What feature will show you all the modules that were loaded before the current one? It's one way to trace how you got here. Which one will show all the functions that are currently waiting for execution to return to them? That's a stack trace. Everything that is currently executing is got its own stack frame on the stack, and it's waiting. You have a dream and a dream within a dream and a dream within a dream, and they're all on the stack waiting to come back. That's call stack trace is what tells you that. All right, what does the minus sign do? That's a back trace. Just moves the EIP back where it was, nothing else, but you can see where you came from in a very simple way. All right. And which one lets you step back and see previous register values? That's a run trace. More expensive, but more complete. All right. So here we are at 126. And the one I want to show you is Project 11, Hacking Minesweeper, which is pretty good. And I think it's more good practice for you guys. So I made a modified version of Minesweeper, which, by the way, makes it illegal pirate software, and Microsoft might serve me with a DMCA takedown notice, but I don't think they will. But in principle, I failed to get their permission to modify Minesweeper because I'm sure I'd never get the permission. So anyway, so you can download Minesweeper and get MineSam, which is Minesweeper modified a little bit so that there's a secret word when you win the game, which you use to get your points. That's all I did. You can run Minesweeper on your Windows machine. And if you do, let's get rid of all this junk. Okay, I put Minesweeper someplace. Here it is. It comes out as a zip file. You unzip the zip file, and then you have MineSam. And this is MineSam. I'm going to do the beginner level. So you have this little board. This is a game where you click these things, numbers come up, and you can use these numbers to figure out where the mines are. It's a little bit like Sudoku or something. So there's actually a game you can play, and you can do it that way, but what fun is that? The point here is we are going to cheat on the game. So that's the game, and in order to cheat on it, the first thing is, of course, to look at it in Olly. So let's bring it up in Olly. I've already got MineSam loaded here. I'm just going to reload it. Okay, now if I run it here, it runs and up comes the game. So I could play the game here, but what I want to do is understand what's going on inside the program. So I'm going to look at the memory layout. Here's the MineSam. It's got text, data, and resource section. Now the text section is the executable code, the data is the stored variables that change, and the resource section is things like the graphics and the winning victory messages and stuff. So the data section is where I would logically expect the game board to be. So, and it's very small. It's only 1,000 hexadecimal big, which is, I think, like a 64K or something like that. That's why the actual memory segments are really small, and you can often just read them and just look through them to find things without having to do anything complicated. And that's the case here. I can just right click and dump that, and it is not very big. The whole thing is about 10 screens of stuff. So this area right here looks like the game board. You can even see it's like a rectangle. I have 10s forming a square and 0Fs and stuff inside there. So to see if that's the game board, I can just go to the game and play the game some. And now when I click here, see a little area changed. So you can totally see where the mines are here. A 41 is where there's a 1 in the game. There. There's ones, 1, 1, 1, 1. And there's 41, 41, 41, 41. So there's the game layout. It is just 1 byte per square and 1 character for a mine, 1 character for an empty square, something for the edge of the board, and something for the number. So you can totally cheat by just looking at memory. And you could just read this to figure out how to cheat, but we can be cooler than that. What I want to do is make a pretty board that lays it out correctly. And to do that, I'm going to do it with Python. There are many, many ways to do it. But I use the tools I know, and what I mostly use here is Python. So you need Python on Windows. I've already put it in the virtual machine you're using, and you can add it to any machine you want. Python installs on any OS. It doesn't install very well on Windows. You have to follow my instructions and make a symbolic link. It'll install, but you'll only be able to run it from 1 folder by default until you make a symbolic link. So notice in the game board, there is a way to spot where the game starts. The 10s are the edge of the board, and before the 10s there are some numbers. 0A, 09, 09, and 0. 4 32-bit integers are stored with the right. And one of these I think is like the number of mines, and that's why I kept hoping I could change it effectively, but not to get my goal done. But the point is, this is a way to spot the game board, because one thing, which is pretty annoying, the game board is not always at the same location in memory. Even when you don't relaunch the game, you just make a new game, it moves. I don't know why it moves. I found that very annoying. I originally wrote my hacking tool to just look at a certain offset, and it didn't work. So you have to actually hunt and find the game board. And this is how I find it. I look for this series of 20 bytes. That series is close enough to being unique that it seems to work in practice to hunt for that. So all you have to do now, so the first thing you have to do is dump the process memory. Now, I did not know that you could use OllyDbg in a command line mode. I just saw that in the slides now. I didn't figure that out. That would be pretty cool. If I could run OllyDbg and dump just the data segment, I would get a really small file, like just a few kilobytes. It'd be easy to hunt through. But I could not figure out how to do that with any tool I could find. I went to Microsoft and got ProcDump, which is the tool. The point of ProcDump is so you can sell people software, and when it crashes, you can tell your customers, run ProcDump and send us the memory dump. We'll figure out why it crashed. That's what it's for. It is not intended to dump just a little bit of the memory from your process. It's intended to dump enough so you can fix the code. So it has one small dump, which is a mini dump that just has like handles and doesn't have the data, and has another one that's all memory, and that's about it. There's one in the middle, but it totally doesn't work very well. So the only thing you can do is dump all the memory with ProcDump. And so you can, ProcDump minus MA will dump all the memory, which is like 90 megabytes, which is still not enormous. I spent like a whole day trying to avoid that because it just seems so wasteful to dump 90 megabytes when I really only need 1 kilobyte. But really, 90 megabytes isn't the end of the world, and I finally just settled for that. So if you run this thing, you can do a ProcDump of the running process. All you need is the name of the process, and then you tell it the name of the file you want it to put it in. I called it mine, and it will create a file called mine.dump, which is 90 megabytes big or 70 megabytes big, something like that. And so let me do that. Go to so here's my Olly. I'm done with OllyDbg for now. So I'm going to nuke OllyDbg. And that kills Minesweeper, so I'm going to reload Minesweeper. Okay, now I've got a process. Now, if you want to see by the way, you can do this in Task Manager too. If you go to Applications, you will see MineSam. And if you go to the process, it will show you that's showing me Explorer, which is kind of weird, but there is a MineSam process here. You can dump memory from right here. Create dump file. And that's essentially all that ProcDump does. But it does it from the command line, and I want it from the command line so I can script it. But you can totally dump memory here for the purposes of debugging things, and often you do when you're trying to fix things that are making your machine crash or making it run slowly or something like that. Anyway, so to do it from the command line, I open the command line. ProcDump is a sysinternal tool from Mark Rusinovich, and it dates from the old days of MS-DOS. He always writes very simple tools that do not install anywhere. They don't make shortcuts. They just live in a folder, and you run them by typing the command line in the folder. This is intentional, so his tools have a small footprint. They don't modify the system, and you can use them easily. So you have to go to where you put it. I downloaded it onto my desktop, I think. Maybe it's, let's see. Nope, I must have put it in my downloads folder. Okay, /downloads. And let me make my font bigger. All right, so here I am. I'm going to, this is where I live, and I can do ProcDump. Go to my instructions. There. Do it from downloads, ProcDump. Okay. So see proc. Okay. There. There's procdump.exe. Here's my old mine.dump, which was 38 megs. One thing that is sort of baffling to me is you run this, you get randomly different sizes. It doubles and shrinks. I go sometimes. One of them would give me sometimes 2 megs, sometimes 4. This one gives me sometimes 35, sometimes 70 megs. I don't really know why. Now I'm going to remove the old one, MineStar. Oh, I keep doing that. This is Microsoft, not Linux. So it's Dell. Okay, now I can do a ProcDump, and a -MA will dump all the memory from the file called MineSam. .exe. I think it's MineSam. Let me check my task manager. It's minesam.exe. That's the name of the project. Okay. And then the name of the file created is going to be mine. And it will, 38 megs is the size of the thing it's dumping out now, and it adds a .dmt file extension to it. So you can examine that in a hex editor like HXD to see what you've got. And remember, we were talking about this in the lecture. The addresses don't really map. If you look at the address in Olly, it doesn't really match the address in the dump. And it won't really match the address in the EXE or in IDA. Each one of them takes the segments and puts them differently. Usually the low order bytes will stay the same, but the high order bytes will change as the whole segment is somehow in a different area. So what I do to find the board here is I just search for something. And you could search for that string we're going to use. One thing I like to do is just search for the edge of the board. I know when I get there, it's going to have 10s on the edges and then F's inside. F is an empty cell and a 10 is the edge of the board. So I search for the hex value 10, 10, 10, 10, 0F, 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 0F. That will usually find it. And it found it the first time here. I can tell because it's going to be this junk here, which is all empty cells. It's got 10s here, and before that, it's got the 9, 9, and A, these hex values. That looks like the real game board. I think it's here at that address. So I've seen what it looks like. Now, all I need to do is automate this stuff and then make it pretty. And you can do that with a script I wrote, which you can just copy for the first part. The first part, you can just duplicate my work. Later on, you're going to have to make your own. So first, I have cheat.py. To give you a start, I gave you a cheat to working from. This is cheat.py. Let me make my font bigger. Okay. So if you have not written Python scripts, the point of this should add to your tool chest. This is how you do it. This is how everybody does it. You don't really know programming. You just go to one of those things, what is it, Stack Exchange, and you find a sample and you modify it, which is perfectly fine. I'm happy with that kind of coding. So I give you one so you can work from it. So what this does, I import OS, is the only Python library I'm going to use, is one of my favorites. OS lets you run DOS commands from inside Python. So you don't need to figure out how to do anything in Python. You just figure out how to do it in the command line and you can run it. So I'm going to run procdump minus MA by this way. First I have a command to delete the old one. Then I have a command to make the new one. This is the typical sloppy, hacky code I always write. If it's not there, this will create an error. I don't care. This will run anyway. It'll make a new one on top of it. Now, I'm going to find the game board. So I just made a mark, which is the thing to look for. A0009000 and so on. It's 20 bytes long. So this is how you do it. I just got this from, of course, Stack Exchange, how to open a file and read in Python. You do with open file name read binary as F, then fread, however many bytes. So first I read 20 bytes to get started. Now, as long as it hasn't found the board, it's going to read one more byte and take 19 bytes of what it used to have and add the new byte to the end. So it's going to have a rolling group of 20 bytes in this thing called C. It reads this, so it's going to, it calls it line. Right, line equals fread 20. Line is going to be the first 20 bytes. Then, if it hasn't found the board yet, it's going to read one more and take the whole line. This is a great thing about Python. In Python, if you have a string variable, you can take a substring very easily. So if you go from 0 colon, that's the whole thing. If you go 1 colon, that's skipping the first character. So I skip the first character, keep the remaining 19 characters, and add the new one to the end. So I moved my group of 20 characters down by 1 byte. Now, I increment number red. If the number red is big enough, I'll just print it out so I can see some progress so I don't get bored waiting for slow things. And then if it equals the mark, then you found the game board. If it doesn't equal the mark, you take another byte and just keep going this way. Python is extremely fast, so you can do sloppy things like this without bothering to jump forward by 4 bytes at a time or anything, which probably would be more efficient, but I just don't care. This, in fact, only takes a few seconds to hunt through 70 megabytes, so I don't have to bother making it smarter. So that's how I find the game board. When I find the game board, I keep the last 4 bytes of the thing before it, pretend which are actually part of the game board. And then I take 500 bytes after that and add it in. So I have a lot of stuff in the area of the game board. I didn't even bother to make it the right size or anything. I just grab a bunch of stuff. Then I just sort of looked at it and did trial and error until I found what the game board is. So a 10 is a dash, that's the edge of the board. An F is a space, that's an empty cell. An 8F is a mine. I forget what a 0 is. 0, I made a space. And this one here, they use a 41, which is an A for a 1, and a 42 for a 2. but the ASCII for 1 is 31, and 32, it's 16 less. So I don't know why they did that. They use an A for 1, so all I have to do is subtract 16 from those numbers to turn letters to turn them back into numbers. And that's all I did. These seem to be enough cases to handle everything that happens that I just build strings line by line and print them out. That's all this script does. It is very simple, very easy for you to understand and easy to modify, which is what you're going to have to do, because this only works for the easy level. So that's cheat. So here's my game running, and all I have to do is run that cheat. So Python, cheat. Got to spell Python better though. Okay, it hunts, it finds the game board, eventually, there, and then it prints out where the mines are. So now I can play the game with knowing where the mines are. So I'll just zoom in here to see. I can see there are no mines in the top row at all. So I can do that and that. There's no mine. Oh, this is the right-hand row. So there is a mine there, but never anywhere below that. So I can just go down here, all these. Now, if I don't want to try to continue, because it's getting kind of hard to see the grid here, I can now cheat again. Now I've got some of the information. I just run my cheat again and get the current state of the board. Okay, now I have the 1s and 2s that I've already found visible, and the 0s visible, so it's pretty easy to zero in on what else to click. So you have to win the game, and then the win message will have a thing you put in to get your points. And then you got to try to win the game on intermediate level, which is bigger, and your script will not work. You will have to modify and make another script that cheats on this game. And my plan was for you to then do expert mode. And when I did it, I wrote a cheat script for expert mode, and I still couldn't win. I don't know what the hell happened. One thing is it took me a really long time even when cheating, and I think maybe I was unable to get the fastest time. I think maybe somehow I broke something when I was modifying it, although I did very little modification. But anyway, there is a win message for the expert level, which has another code that's worth more points to you, but I can't get it out of the game at all. And so I took it out of the project, and then I thought about it, and I said, no, I'm putting it back, because you just have to use another technique, which I leave as an exercise to you. There are other ways to get the message out of the program without winning the game. So this is the required part of the project is the one where I totally tell you how to do it. All you have to do is follow the steps. And then there's 2 levels of extra credit. The first level is modify this and cheat on the intermediate level until you win, and this technique will work. And the third level is find out what you would have gotten if you won the expert level, which I think is impossible. In my experience, there is no way, no matter how good you are at the game, to actually get the win message out of the expert level, but you can still get it out of the program. So find it, and you find the secret word, you get the points. So I figured that would be a good set of projects to give you some practice. And this is all, you know, we're supposed to be able to take a random executable and figure out how it works, whether we can run it or not, whether it's malware or game or whatever it is. Games are a perfectly fine place to practice as far as I'm concerned. You're just learning how to use all these tools to figure out what you've got when you've got a fragment of code. Anyway, that's what I wanted to show you. Got any questions about anything? Well, I'll just clean up. I'll go to the lab and help anybody who wants help over there. Now, by the way, if anybody wants to volunteer to open the lab, let me know. I don't have enough volunteers, and some of my volunteers are not showing up, so people are getting frustrated coming to the lab. So if more people want to open the lab, that would be good. Anyway, I'll clean up and move up there.